Good afternoon, everyone. Thank you for joining me. Today, I will be presenting the topic co-pyrolysis of marine plastic waste and biomass to create fuel in coastal Florida. Florida faces two major challenges, one of which is a reliance on fossil fuels for energy and the environmental burden of marine plastic waste, as well as biomass accumulation. These issues not only threaten ecosystems, but also contribute to the greenhouse gas emissions and inefficiencies in waste management. Co-pyrolysis offers a dual solution by converting marine plastic waste and biomass, such as beach wrack, into renewable biofuels. Florida's abundant feedstocks and unique coastal conditions make it an ideal candidate for this technology, aligning it with sustainability and energy goals. Florida's dependency on fossil fuels and these inefficiencies, as mentioned, highlight a need for this sustainable solution. The research aims to assess the feasibility of co-pyrolysis, optimize the conversion process for biofuel production, recommend policy and community strategies to support its adoption. It also investigates critical questions such as environmental impacts, economic viability, and overcoming regulatory barriers. Co-pyrolysis combines plastics, which are hydrogen-rich, with biomass like beach wrack. This synergistic process improves the yield and quality of bio-oil, biochar, and syngas. Marine plastic waste is a global issue with limited recycling options. Beach wrack is an underutilized biomass resource. These can both serve as excellent feedstocks for co-pyrolysis. Environmental benefits include reducing greenhouse gas emissions, avoiding harmful byproducts like dioxins, and creating biochar for carbon sequestration. Economically, co-pyrolysis generates revenue from multiple byproducts while addressing waste challenges. This study uses a qualitative, theoretical approach based on secondary data due to the duration of this study here. The methodology involves a comparative analysis, environmental impact assessment, economic feasibility assessment, and a policy review. The results highlight the transformative potential of co-pyrolysis. So as far as technical feasibility goes, co-pyrolysis increases bio-oil yield by 20 to 30% and improves energy density through synergistic effects. Environmental impacts include reducing greenhouse gas emissions by up to 50%, diverting significant waste from landfills, and minimizing harmful emissions like dioxins. And as far as economic viability goes, it generates multiple revenue streams from bio-oil, biochar, and syngas while utilizing locally available feedstocks. Despite these advantages, there are challenges including feedstock variability, initial capital investment, and regulatory hurdles. There are a few recommendations here. To advance co-pyrolysis in Florida, I would recommend launching pilot products to test its feasibility under real-world conditions, conducting a life cycle assessment to quantify long-term benefits, streamlining regulatory processes and providing financial incentives like grants and tax credits, building public-private partnerships, and finally, engaging communities through education campaigns. In conclusion, co-pyrolysis is a very promising solution for Florida's dual challenges of waste management, and renewable energy. It offers environmental benefits, economic viability, and supports the transition to sustainability. By implementing pilot projects, policy reforms, and community education, Florida can position itself as a leader in an innovative waste-to-energy solution. Thank you so much for your time, and I'm happy to answer any questions.